Okay, let's start. Okay, so no quiz and then not many students. I realized it just now. Okay, so yeah, just let's quickly address these questions. So we discussed about this. I think it's a max pooling part of done before like a one-by-one conf, and we discussed about this max pooling with an overlapping windows, and in practice, I mean in principle, the number of parameters for the max pooling, I mean there is no parameter to learn, so I'm not sure. I mean I don't understand this question honestly, but the max pooling done before this one-by-one conf in the inception module doesn't increase the activation map size, nor it doesn't involve any kind of parameters to learn. So computationally, I don't think it's too much. So if you still have the question, please let me know after the class. And also, I think we addressed the last question. So in the case of let's see. Okay, so in this case of multitasking learning, which has a different units in terms of their measurements. For example, this softmax loss. Yep. Do you guys know the unit? So what is the unit for this softmax loss, or cross entropy, or entropy, or K divergence? Although we don't care too much about the actual unit of this loss measure, but that unit is actually bits. Okay. And also, have you heard about this net? So it's like log 2 of 8 is 3, right? So to represent this number 8, we need 3 bits of, in the binary number representation, right? So in the case of entropy definition, so the entropy definition is like something like this, right? So it is like the expected value of negative log pi, right? Because for this measure we are giving the weight of pi, so it can be viewed as the expectation value of this particular function of pi, which is a minus log pi. So this guy can be also viewed as having the unit as bits. Okay, so that way this entropy or cross entropy and like the softmax loss, because they are all involving this log stuff, so it can be viewed as having the unit of bits. And what is net? That is in case of using, so in this typically we use 2 as a basis of this log. So in that case the unit becomes bits, but if it is becoming e, which is a kind of a natural number, I forgot the name, but when what is this acronym for? So it's a natural log, right? So that way this net is like a natural kind of a number of bits. Okay. But anyways, so this has the unit of bits, although it is not that much important, but and also in this case, this is typically using the L2 squared loss in terms of the pixel differences. right? So if we predicted the regression, the bounding box as this position as maybe 10, 5, and then the actual ground truth should be here as maybe 8 and 6, and then we have two pixel differences, right? So so here the pixel squared is the unit, right? So in that case, how we balance between them, or how we actually assign the hyperparameter assigned to the second loss, for example, how can we set that parameter in practice? So in this case, you have to actually you have to try out some particular, randomly chosen value of an alpha, and then you can draw each of the loss over the training, over the iteration. So if we go through our iterations, and then this softmax loss is becoming like this, and then this L2 loss, there is a kind of two different versions of this measuring this L2 loss. The first one is without alpha, and the second one is including the alpha, right? So let's call this second one before multiplying with the alpha, and then draw this, okay? And then that is, for example, like this, okay? And then suppose alpha was set as maybe 1,000 in the current training stage, and then like alpha times the regression loss will be like this, right? So from the perspective of our objective function, which one will we focus on minimizing? Of course this guy, right? Because it is, in terms of their scale or relative like magnitude, the second loss that is multiplied with this guy, right? So first one times second one, but when viewing them, these two are added together to to compute the single loss, right? And so if this guy is much bigger than this first one, and then our training objective will still focus on the minimizing the second one, which means that we want to reduce this graph much more, right? So in general, between this guy and this guy, if their scale of this guy and this guy is becoming a little bit kind of comparable, okay? So that's how we balance or adjust our parameter alpha. So alpha is too small, okay? Alpha is too small, and then so the this part is like really small, and then it means that our training objective will just simply ignore this part, because like 0.001, and then this guy, even if we don't care about it, then that will not be a big value, so that will focus on the first one, which means that in that case we will only focus on correctly classifying the image, but not correctly predicting the bounding box. So so this is a kind of the most straightforward way of monitoring these, and then having an idea or sense about how to adjust this parameter alpha. But but alternatively, you can also use more kind of meaningful kind of measure to monitor the behavior between these two tasks. So so this is the first one, and this is the first one. So first one is the softmax loss, right? But more meaningful kind of measure is like training accuracy, right? Or training error. So if we have 1,000 training data, currently how many data items we correctly classify, or how many data items we misclassify, okay? So in that case, it can be measured as a kind of like a relative measure of maybe 80% or 90% of the accuracy. Okay, so if we consider this accuracy graph, and then suppose this one is our accuracy graph for the classification task, and then suppose our training accuracy is 80%, for example. Okay, and then also we can draw another separate graph that actually measures the performance of this regression loss. So in this case, if we compute this L2 loss, like this guy, L2 loss, so it's the squared sum of the difference in terms of pixels of x, y, and w and h, right? So in this case, yeah, we can actually measure separately for each of the x, y, w, and h. But if we just sum them up, and then it is just measured in the squared form, and then take the square root of it, and then it will give us an idea about the average error that we are making in predicting, at least for the training data, the amount of the error in terms of number of pixels, okay, when predicting this point and the width and height, okay. So in that case, if the pixel, the average error in terms of these number of pixels, if it is too high, for example, it's currently like, so it should be reduced as the training goes on, and then the average pixel difference or error is like maybe 150 pixels, which is a lot, right? If the image is maybe 300 by 300, and then prediction error is 150 pixels, and then it is really a lot of an error, right? So it's not. It means that we are not correctly predicting or estimating the bounding loss. So in that case, it's time to focus more on this guy. So in that case, we can increase this alpha a little bit more, right? And also in this case, for this guy, the first scenario, we can actually overlay these two graphs into this single panel, right? Because even though they have a different unit from the beginning, but from the perspective of a loss function or our optimizer, our loss function is anyways the sum of these two parts, right? So the actual values actually matter, right? So that way we can draw that in the same kind of graph with the same kind of y values, right? So we can it actually makes sense to compare between the values of this guy and this guy. But in this case, it cannot be drawn in the single figure because in this case it's a classification accuracy, and this guy is the pixel difference as our error. So they have inherently have a different units. So it does make sense to draw them in a single figure. Does it make sense? So it is not the only answer. So you can be kind of creative to analyze or troubleshoot the current status of your training algorithm or model against some potentially noisy data and so on. So the task gets more complicated, and so you can do more things to analyze what the problems are currently. Any questions about it? Okay, so I believe I answered the second question. So if I haven't, please let me know. Okay, then mask RCNN. So let's briefly go through some models for the detection. So although the lecture didn't cover the entire details or full details of all the algorithms like faster RCNN or faster RCNN and things like that, but at a high level, you can, it's important to get some differences between different models. So we have, initially we have an RCNN, right? And then after then, Okay, so we have this fast RCNN. Okay, so what's the difference between fast RCNN and original RCNN? So we have the module that obtains the ROI region from this region proposal module, right? So we have the module that does this region proposals, right? So given a certain image, and then we already have some predefined, some simple algorithm that can produce all the potential candidates that might, that can include some objects. Okay, so per image, around 2,000 different bounding boxes or regions, or region of interest is proposed, and then for each region, we actually crop that image, right? And then we just go through our convolutional neural net, right? So that is the original RCNN. And in the case of a fast RCNN, we still apply this region proposal method with no changes compared to just the RCNN. Okay, so so these regions, proposed regions or ROIs are obtained by applying the region proposal method on the original image, right? But here, once obtaining this region proposal, and then the previously, we actually crop that region, and then that will be given as an input to our CNN, right? So for each of our 2,000 ROIs, and then we have to run the CNNs to obtain the feature map for that particular ROI, 2,000 times, right, separately. But in this case, given this a single image, before applying the region proposal method, we just go through the convnet to obtain some feature map like this. Okay, so this is our feature map, and then still this region proposal method is applied to the original image, and then once obtaining this specific region information, and then we actually crop that part from this this activation map. Okay, so here we actually crop this part. Okay, so in this way, we actually avoided the repetitive computation of having to just give this separate regions into the CNN. Okay, so here the main idea is if if the two ROI regions were computed in this form, okay, so certainly they have an overlap, right? So for this part, when separately giving it to the CNNs, and then CNN will have to compute the feature vectors for this common or same regions twice, right? So that way we have some computational redundancy or inefficiency. See, so that way we just pre-compute this activation map, and then we crop that region proposal or ROI regions from that activation map. 네.
리전 프로포즈를 피처맵에서
네, 그러니까 피처맵에서 이렇게 크롭을 해오는 거고, 근데 저 리전 프로포절 메소드는 아까 얘기했듯이 이 오리지널 이미지에서 돌아가는 거예요. 네.
오리지널 이미지의 위치에 있는 거.
그렇죠, 그 위치에 있는 걸 갖고 온다.
피처맵에서 해당되는
네.
위치에서 빼오는 거.
네, 맞아요.
계산은 어떻게 해요?
어떤 계산이요?
피처맵에는 오리지널.
네, 이게 또 좋은 질문인데. So typically, as far as I know, I might be wrong, but as far as I know, this convnet doesn't involve any kind of downsampling, or so it basically preserves the spatial resolution. Okay, so in that case, the width and height that this original image has will be preserved or stay the same in this activation map. But also even if we involved some of these max pooling or this downsampling steps, we have some ways, because yeah, if it is like this region, and then if this image was downsampled into like maybe 100 pixel by 100 by 150, and then for example this guy was downsampled by the ratio of 4, and so 100 became like 25, and then 150 became like 30, although it is not standard because the ratio now became different, right? But now in terms of this y-axis, it was downsampled by the ratio of 4, and then it was downsampled by the ratio of 3 along the x-axis. But still we can we can actually obtain the corresponding part for this region, because for this part we just downsample it by the ratio 4 and the 3, and so we can still obtain this guy. Any other questions? Okay, so in this fast RCNN, after cropping this activation map, and then we will just do the fully connected layer to directly regress or perform this regression on the bounding box. Okay, and so here, have you guys understand this ROI pooling? ROI pooling. Why do we need this ROI pooling? What's the meaning of it? So it is also the same as this warped image regions. So so here in this scenario, the bounding box can have a different size and different aspect ratio, right? But when giving it as an input to our CNN module, then the CNN should take the fixed size of an input image, right? So simply the ROI pooling is to just resize this image into a fixed, predefined, like fixed size of the input that will be given to this component. Okay, so basically this ROI pooling, you can just think of it as a kind of resizing operation. Okay, but this resizing is sometimes not easy or not that straightforward. So in the case of this 4x4 images into maybe 2x2 images, okay, so in this case we can just do the average pooling to resize this image, right? Okay, but what if we want to sometimes increase? So y has currently 4 pixels, but what if we want to have a 7 pixels? Okay, and also we have 4 pixels, but now we have like 3 pixels. Okay, so it's like you can imagine like this opposite process, mapping this guy into like maybe some square size, the square shape of the input image as an input to the component. But how can we deal with this situation? Okay, so so there are several simple algorithms that can perform this a little bit nicely, and so one of them is called bilinear interpolation. So basically the idea is really simple. So we are just doing the interpolation. So suppose this guy was 1 and the pixel value was 5. Okay, okay, so this first pixel can be viewed as like, so it had a width of 1 or the unit of this pixel, but now this 1 became like 1.75, right? So our pixel became larger, that has the height of 1.75 because that is the ratio, right? Okay, and then this 5 is starting from 175 and 3.5. right? So that's the simple computation of expanding it by the exact ratio. But we need the pixel-wise, pixel values basically. That is at the integer position, like. So if we think of a regular grid that is formed by our integer form of a pixels, let's see. So like this. So this is the first pixel, and this is the second pixel, and this is the third pixel, and this is the fourth pixel. Does it make sense? Right? Okay, so let's think of this second pixel. Second pixel. The second pixel has the first pixel with the amount of 75% and 25% of the second pixel, right? So that way we can actually do the linear kind of interpolation or weighted average between these values. So it means, so originally this pixel value is 1 and this pixel value is 5, right? So 1 times 75 and 5 times 0.25. Okay, so that way we do the weighted average, right? So that will be the pixel value corresponding to the second pixel. Okay, so that's quite reasonable, right? So that is called the linear interpolation. Okay, linear interpolation. But why do we need this bilinear interpolation? Okay, because we basically have a two-dimensional array, right? So one single pixel is not just divided by these two pixels, but it is actually divided by like 4 different regions in this case. Although in this so in this case, in terms of this x-axis, it will be shrunken by the ratio of 75% because we have 4 and the 3, right? So in the case of this x-axis, right, the pixel on this part, okay, that pixel is like invading that regular grid, right? So in that case, one single pixel can be divided into like this, right? So originally it was from the 1, 1 pixel, right? And this guy was coming from this guy, right? And this part is coming from this, and this guy is coming from this, right? So it's like, linear interpolation or weighted average of these 4 different values along the x-axis and the y-axis. So, I mean, I will just give this kind of intuition, but if you just write the formula for this, and then you can easily see that it is actually kind of linear in terms of like along the x-axis and the y-axis. So we have 2 axes, and so we call it as a bilinear interpolation. Okay. So this kind of bilinear interpolation is actually quite used a lot. So if you, we studied on unpooling, right? Or like upsampling, right? So one way of doing the upsampling is just, let's see. So this is a one way of an upsampling, right? And this is the second way of an upsampling by remembering the max value position in the encoding part, right? So from here, so we remember during our encoding phase, we remember where this max value was placed, or basically the position of this max value, and then we just give it to that corresponding max value position during the encoding phase, right? Okay, so in this scenario, we didn't think of like non-integer kind of ratio between these two images. So we always expanded the 1 pixel to maybe 2 by 2, which is still like an integer ratio, or 3 by 3 in case of we just upsample it by the ratio of 3, right? So in this case, if all are integer involved, and then yeah, the scenario is simple. But what if we just do the upsampling with a non-integer ratio, and then we can just apply this bilinear interpolation on this activation map, right? So it's quite obvious. And this bilinear upsampling, so does it involve any kind of a trainable or learnable parameter or not? It doesn't, right? So we have a fixed rule, right? So in that case, yeah, we don't have any kind of learnable parameter for this bilinear interpolation layer or bilinear upsampling layer. So yeah, at least so far we studied several different upsampling methods. So the first one is this naive method of just copying the values onto the expanded patches, and then this a little bit more advanced one, which still doesn't involve any trainable parameter, and also alternatively we just studied this transposed conv or deconvolution, which definitely involves the trainable parameters, and also now we studied the additional upsampling method of this bilinear interpolation method. But this bilinear interpolation is not restricted to upsampling, but it's also used in the downsampling part, right? So because we are studying like detection and semantic segmentation and instance segmentation, so yeah, in general, this mask RCNN is probably the one of the state-of-the-art method for the instance segmentation. Okay, and for the detection task like SSD or YOLO is probably the fastest one with a decent accuracy. But if you can just bear a little bit kind of a slow speed, but you only want the maximum possible kind of accuracy for the detection task, and in that case, the faster RCNN is your choice. Okay. So for example, like in a medical imaging case, we want to like obtain the detection region of some disease, like some kind of lung cancer or some abnormal kind of tissues and so on. So we want to perform this detection task, but we don't care about the speed or kind of real-time response, but we only care about the maximum kind of accuracy. So in that case, the faster RCNN is probably the best choice. But if you want to do like a video detection and tracking and things like that, and then real-time aspect is really important. So in that case, YOLO or SSD is your choice because it's relatively much faster than this faster RCNN. And what about the semantic segmentation? Okay, what's the best method for the semantic segmentation? So there is a method called DeepLab. So probably this is a one of the state-of-the-art and probably the most widely used semantic segmentation network architecture. Okay, so I'm not gonna explain it in more detail, but in the case of this DeepLab, there are several different versions. So originally we have a DeepLab version 1 and version 2 and so on. So in the case of like DeepLab, I believe version 3. Let's see. So in this DeepLab, there is a kind of an interesting module called the pyramid pooling or multi-scale convolution stuff. It is quite an quite interesting concept. But anyways, I'm gonna give you some idea of like, so if we do the semantic segmentation, the network architecture is exactly like this kind of encoder-decoder architecture. Okay, and in this figure, the left part is the encoding part. So image gets through the convolution layer. Although we do some interesting module called the spatial pyramid pooling or SPP. But anyways, we can you can just view it as obtaining the encoding, activation map as the output of this encoder module. So this rectangle on the top left, okay, that is corresponding to the activation at this position, at the end of the encoder phase. And then now it's time to perform the decoding phase, right? So we are doing the decoding, right? And then for here, we see this 4x and 4x. It's like upsampling by the ratio of 4, okay? So given the particular spatial resolution of our encoder output as an activation map, and then we just upsample. We want to increase the spatial size by the ratio of 4, right? So in this case, if we use the deconvolution layer, okay, like this kind of deconvolution layer, this decoding part will also have a trainable parameters to define our deconv filter coefficient, right? So in the case of a DeepLab version 2, or maybe previous one, I believe, so they actually adopted this decoder part as the deconvolution layer, which involves this trainable parameter. Okay, but in this case of DeepLab version 3, so they just replaced this deconvolution for our upsampling with this bilinear upsampling. Okay, so now this decoder part has no longer any kind of trainable part, right? It is just simply upsampling using the bilinear interpolation and upsampling the bilinear interpolation, right? But here, we have some interesting architecture called. So let me explain this. So in this decoder, encoder-decoder of this image, whether it is a semantic segmentation or maybe some image translation or the colorization and things like that. So just to see. Did I show this example? Ooh. Oh. Okay, so it's a little bit. Let me reset it. How do I reset it? Okay, so it is basically the colorization application. So here it is still like taking the input as an image and giving the output as another image. But now, we have a input as a grayscale image or this kind of outline. Only the major lines that specifies the object shape, and then the output is fully colorized version. Okay, so in this case, we just apply. We utilize this encoder-decoder architecture. So if we want to change this part, so it's part of like user interaction that gives us additional input to our encoder-decoder network. So although the color is not that pretty, but you guys get the idea. So it will reflect user interaction or user intent, right? But here, this deep learning module actually did some intelligent job of this colorization, because we only gave this scribbled form of our line, that this line should at least have this blue color, and then it recognizes some semantically consistent part of like the flower on the hair, and then it colorized that entire part using that color. Okay, so the reason why I kind of show this is because this kind of image, input is an image and output is still having the same resolution, same spatial resolution. We still use this encoder-decoder architecture. But one of the effective architecture that is added on top of this encoder architecture is called UNet. Okay, UNet. So yeah, if you maybe work a little bit on this similar kind of problem domain, and then UNet, you might have heard about this UNet in many different kind of similar tasks. So UNet is because, yeah, the name of this called UNet is because of this kind of architecture, because it has a U shape, right? So in this case, it is actually an encoder-decoder architecture, right? But we basically have the residual connection over here, okay? So back to this architecture. Okay, so we have we have some correspondences between this and this and this and this, right? In terms of the symmetry. So we basically add the residual connection, or this dense connection that was used in the ResNet and also in DenseNet. So we have this encoder kind of activation map, right? And when doing the decoding part, I mean decoding module, and then we basically add this guy onto this activation map. So basically, between the encoder-decoder architecture that have a perfect kind of symmetry, we basically give the activation map that was generated in the middle of our encoding module, and then we give it to the decoder part at the corresponding layer. Okay, so we can have a kind of we have two different choices. The first one is just simply add this encoder part into here, but also another choice is just concatenate that into the decoding part, right? Okay, so I believe the original UNet architecture is using this residual connection that actually adds those two activation map into one. Okay, so in this case, yeah, this encoding phase, this is our activation map. So why is it like drawn? Why is it drawn in this way? I mean, it's just up to his choice of drawing their architecture in more interesting way. But in this case, it is like a sequence of convoluted. Okay, and then for here, it is performing the downsampling using a max proof. And then do some several stages of convoluted, and then do some downsampling, and so on, right? And then now it turned to the decoder part, decoding phase, and then so activation map over here is actually added to that activation output in our decoding phase. Okay. So in general, this UNet the main reason for this UNet architecture, or this residual connection, is so effective is because it is known that this UNet architecture is really effective for preserving the edge information. So it is a little bit difficult to explain, but so we are given a big image, large size of a spatial resolution in our image, and then we downsampled it, and then at this point we basically we lost some amount of a spatial resolution. So we don't actually differentiate. We cannot differentiate like this edge like was over here, or maybe over here. We found we found some bird, or some kind of edge information like this of some shape or some object, and then due to our max pooling operation during the encoding part, if I mean these detailed edge information or exact kind of edge position will be lost when doing this encoding part, right? Because we are doing the max pooling or downsampling it, right? And then using that information, we now start our upsampling, right? And then if you imagine like a semantic segmentation, like this, okay? So let's imagine this image was encoded into much smaller kind of downsampled images, and then we want to reconstruct its full resolution, like a full pixel level, pixel level classification or semantic segmentation tasks like this. So if this kind of nice edge should be drawn exactly following this boundary between the sky and the trees, right? But how can we recover or reconstruct this, like exact information about this position in terms of these edges, right? So in this case, encoder part, encoding output, due to this downsampling, we may lose this detailed information, right? And then using that, if we decode it into the full resolution, it may be almost impossible to reconstruct the exact kind of position of these boundaries. So in this case, if we use this unit architecture, and then at this point, compared to this, it will preserve more spatial information because it was just, it has a larger spatial resolution than this, right? So in this case, we just give this information at the almost last part of our decoder part, and then the edge information or the exact position information was maintained over here. And then after going through this, and then it may lose a lot of these detailed information, but if we just give it to the decoding part, and then we may give the corresponding decoding layer with the more kind of spatially like exact or correct information. Okay? So that's the main intuition of the effectiveness of this unit architecture. Any questions? 네.
그 맥스 언플링 할 때요.
네.
인덱스를 저렇게 레이시오가
이거요?
일정하게 인티저이면은 그 인덱스를 가지고 가서 거기다 할당을 해주잖아요.
네.
근데 바이리니얼 인터폴레이션 하는 경우에는 그 인덱스를 그 해당하는 부분을 다 가지고 가는 거예요.
바이리니어 인터폴레이션은, 그러니까 이거는 하여튼 이 인코딩 할 때 앞단에서 이제 맥스가 어디서 나타나는지를 기억을 해놨다가 이제 고값에다 이제 이렇게 하는 거잖아요. 그게 이제 맥스 언플링이었고, 그 다음에 이제 바이리니어 인터폴레이션은 그냥 이게 있으면 그냥 이거를 4x4로 이렇게 만들 수 있죠.
근데 그
네.
지율이 정수가 아니라 실수면
그러니까 실수일 때도 이제 그 아무 문제 없이 사용이 되는 게 이제 바이리니어 인터폴레이션이고요. 인티저일 때도 뭐 당연히 사용될 수가 있겠죠. 인티저일 때는 이게 뭐 사실 별게 없는데, 인티저일 때는 이게 이렇게 된다라 그러면 이제 요 픽셀, 이 픽셀이 여기서 이제 2배로 늘어났을 때 어디에 대응되는가를 보면 정확하게 이쪽에 대응되죠. 그러니까 요 픽셀은 이제 이 픽셀만 가지고 있으니까, 바이리니어 인터폴레이션은 어떻게 보면 그냥 복사하는 거랑 이 인티저 이거에서는 아마 동일할 거예요. Any other questions? Okay, so in general, okay, so let me get back to our fast and the faster RCNN stuff. So you now get the idea of the difference of this RCNN and the fast RCNN. And then what's the difference between fast and the faster RCNN? And also, let me point out one thing over here. So in the case of original RCNN, we understand that each of these conv module should take the same fixed size of an input image. So that's why we have to perform this image warping or this ROI pooling which means just resizing it into a fixed size. Okay, so that's the meaning of this ROI pooling. And also in this case of fast RCNN, we just directly crop this part, right? And then what's the next stage? So the next stage is just performing this fully connected layer, right? We don't, we already processed our image by using the conv to extract out some meaningful feature, and then we just crop them based on the result of this region proposal method, right? And then now it's time to just perform our classification, right? Or whether it is a kind of a particular category or not, and also what is the exact bounding box, right? So this is a fully connected layer, and so in that fully connected layer, how do we give this cropped activation map as an input? So in that case, so this guy is all rearranged into a single vector, right? So our fully connected layer will take the input as just a reshaped one-dimensional vector of that activation map. Okay. So in this case, do we need this ROI pooling, for example, like this guy or some different image size, and then it will give us a different size of our activation map, right? And so still we need a ROI pooling or make this image size into the fixed, predefined fixed size, right? Because our fully connected layer is requiring the same number of input nodes, or so the dimension should remain the same for every different, each of our ROI regions of this activation map, right? So that's why we need also the ROI pooling over here. But why do we call this ROI pooling as a layer? I think this in this fast RCNN, they defined their own kind of resizing or upscaling or downsampling kind of a layer. I'm not sure if that layer has some trainable parameters or not, but they defined their own kind of resizing algorithms in the middle of our neural net, or this whole pipeline. Okay. And then what's the difference between fast and faster RCNN? In the case of faster RCNN, this region proposal, or determining, obtaining this candidate regions out of our image is done by the separate algorithm of region proposal method, right? So in this case of faster RCNN, that region proposal module or region proposal method is actually the part of our entire neural net. And this this lecture, or this lecture didn't discuss the details about how this region proposal network is designed and how it is trained and so on, but at least this is now becoming a part of our entire network, right? So you can understand this as like training this region proposal network from the beginning, from the random initialization. So that way, we don't actually need to incorporate any additional region proposal kind of method. Okay. So in that sense, it is more like more of an end-to-end training paradigm, right, compared to the fast RCNN. So in the case of fast RCNN, we used, or we adopted like a separately designed region proposal method, right? So we cannot touch or we cannot modify it like flexibly, right? So that is like a fixed algorithm. But what if that algorithm is like is only suitable for detecting maybe dog and cat, but not for some disease area in the CT images or MRI images and so on, which has a completely different characteristics from the real world images. So in that case, those region proposal method may not work very well for this special type of an image, right? So in that case, we need our own customized region proposal method that can be trained based on our data, right? So that way, this module is trained in an end-to-end manner. So you guys know the meaning of the end-to-end training, right? End-to-end training. See. There was some slide about okay, I'm gonna use my own slide. Okay, let's see. 왜 안 나오죠? 그 컬러 히스토그램 나오고 좀 그런 거 슬라이드 있었는데 CS231에는 혹시 기억해요? 아 여기 있네요. Okay, so I was looking for this slide. So I think it was part of the So you guys remember this kind of slide somewhere in our previous CS231 lecture. So in this case, so given an input image, we want to perform the task of classifying whether it is a dog or cat or maybe a person. Okay, so in that case, before the era of deep learning, before the deep learning was invented, what was the typical approach that people have taken? Okay, so we actually try to try to develop the most smart or the most carefully designed algorithm that can extract out some meaningful information out of this image, right? So one really naive way is to, what's the meaningful feature given this set of pixels in our image? So in this case, we can think of like this kind of color histogram, right? Color histogram, and also, I didn't explain this, right? Anyways, there are several different, methods that were widely used before the era of deep learning, and one of them was this HOG or histogram of oriented gradient, and also like SIFT and SURF and things like that. Okay? So before we utilize deep learning, for example, this SIFT paper was really popular to extract out some unique useful feature. So I want to show give me just 1 second. I want to show this guy. Scale. Okay, yeah. I wanted to show these numbers. Okay, 16,000 and close to 50,000 of a citation. yeah, for example, in my case, yeah, my citation is around 1,000. Okay? I did a research for about 10 years or even more, only 10,000. But this a single paper has yeah, 50,000. Okay, so this is that much, yeah, that much impact at that era. Okay, so yeah. Okay, so SIFT was like a kind of CNN before the era of CNN, and how it works is as follows. So we just split or separate this image into a regular grid, like this small grid. Okay, given this small grid, what we do is, as our feature extraction step, is to compute their gradient. Okay, gradient. 설명 했나요? 안 했어요? Okay, 설명했으면 이야기해 주세요. Okay, so suppose we are considering like the patch over here. Okay, and then we can imagine the pixel values as the z-axis, and then we can think of their like multi-dimensional okay, something like this. Okay, so x and y are our patch, right? And the z-axis, the height is the corresponding pixel value. Okay, so in that case, let's just stand in the position over here. Okay, and then we just compute the gradient. Okay, the gradient. The gradient is basically the steepest direction, right? And so maybe suppose this over here it is a current center position, and then the gradient will point to this direction, right? And then let's relate this gradient with the shape of our image that we are looking at in this patch. Okay. So in this case, if we imagine there the mountain shape, and then the mountain is really high over here, right? Because it's brighter in the lower part, and then it suddenly gets dark, right? Or lower, right? So at this center, what would be the corresponding gradient? Would it be like this direction or that direction? It will be this direction. It is basically orthogonal to our the edge information that we see in this picture, right? So basically, gradient when computing this gradient at this particular image patch, and then the gradient can be used as a edge detector. Okay, the edge is found that has the orthogonal direction to our gradient. Okay, so in this case, yeah, so it is a little bit more kind of a little bit more complicated than I just explained, because in a single patch, can we just compute the gradient at a center point? Yeah, we can actually think of like different position and their gradient, and also, I mean, yeah, there are a little bit more details, but let's imagine like which edges or which direction of an edges are frequently found in this image. Okay, so yeah, I can suppose this is our original image. Okay, and then what will be the statistic or the histogram of our gradient? So if we think of like a regular grid on this image, and then all the gradient will be pointing to like this direction, right? And then let's think of like discretize this gradient in terms of their direction. So for example, the gradient has like this is the first gradient, and maybe having the 30-degree range. So if our gradient falls into this direction, and then we basically add this the count of this gradient by 1. Okay, so like this, and then we have in total 12 different regions, yeah, right, among all the possible gradient directions. And then let's think of the histogram, starting from 0 degree and 30 degree and 60 degree and so on. And then how many gradient did we find out of this entire patch? For example, if we have like 16 different patches, and then we have a 16 different gradient, and then suppose majority of the gradient was found over here, and then maybe over here, and maybe it's over here, and so on, right? So we can think of this a histogram, right, of our gradient, and then that histogram can be viewed as like a, yeah, it is actually called the So do you guys know the bag of words? Bag of words. So this is exactly the same as bag of words. So this, each of our bin is our bag, and then each bin is corresponding to a unique word in our vocabulary. And then if we imagine like a bag of words of vector representation, and then we can just represent, or we can just utilize this multidimensional histogram representation as the image feature that describes this image. Okay, so so that way, basically the statistic or the distribution of this edge direction that was found in in each of our patches in this image, that can be used as a feature vector that can characterize or describe the characteristic of this image, right? And then once we use it as our input feature to describe this image, and then we just perform maybe SVM or random forest or gradient boosting tree and so on, right? Starting from that feature representation. But here, what if our feature extraction scheme just like what I described? So it is called the SIFT. So we just extracted the feature vector as a histogram of this gradient directions by using this SIFT algorithm. But yeah, our task, what if our task, I mean, this SIFT is not, may not be optimal, not optimally designed for our own specific task, right? So depending on our task or the characteristic of our data set, this feature extraction module should be redesigned for the maximal performance. And so this feature extraction part, I mean, when comparing this previous kind of strategy of designing the machine learning that actually focuses on predefined, really carefully designed, but still predefined or fixed feature extraction module, and then the real machine learning actually starts from this position, right? This place, right? And so once image is represented as a feature vector, and then the original, I mean, this machine learning module is blind to this original image, so it doesn't know the actual pixel value or this raw information, right? And so machine learning cannot utilize the abandoned information that existed in our image, right? And so this the main idea of this really outstanding performance of deep learning is that the deep learning actually embraced this feature extraction module as just a part of our network. So if we think of this CNN module, and then we can think of like the very last layer as our main machine learning module that performs the softmax classification or the logistic regression, right? And then all the previous layers can be viewed as this feature extraction. But the main difference is that this feature extraction module is now trained in an end-to-end manner, right? Solely based on our data set. So that is the main idea of end-to-end learning. So that is the main paradigm that that boosted the performance of this deep learning a lot compared to the previous paradigm of machine learning. Okay, so back to this detection module. It exactly follows the same paradigm. So we now embraced this region proposal module as part of this trainable module in our network, right? So that way we can easily expect that this faster RCNN with the more optimized version of this proposal method, we can expect a higher performance of this faster RCNN compared to the fast RCNN. And then so here what's the main difference of this YOLO and SSD against faster RCNN or the precursor or predecessor? So what's the main difference of this YOLO or SSD? So the main difference is that why this the main reason why this detection task is so complicated and so slow sometimes is because we cannot specify in advance the number of proposed regions as an output of this region proposal module, right? So we may get 2,000 proposed regions or maybe 150 for some image. Okay, so in this case, for each of them, we have to perform our detection task of classifying it and also determining its exact bounding box position, right? So although it is really simple, but this variable number of an input and also output, so that is the main kind of bottleneck or main kind of cause of having to this complicated structure of our neuron. Okay, so compared to that, this YOLO and SSD, although it follows almost a similar kind of steps as faster RCNN or the other methods, but here we actually fixed the number of proposed regions. Okay, so that number of proposed region is like defined by b times some predefined spatial resolution. Okay, so if we think of this 7 by 7 as a default proposed region size, and then we can divide this as a regular grid, right? And then for each region, so in this case, what is the number of B? So B is 3. So for each grid, we obtained this guy, and this guy, and this guy. The 3 different versions by varying or by using a different aspect ratio and different size maybe. Okay, and then we may obtain like 10% bigger versions of that, right? And then in that case, our base bounding box will be 6. So in this case, we obtain this bounding box from each of our grid cell. So our bounding box is, the number of bounding box. The number of proposed regions is fixed as that. Okay. Okay, so so for this guy and for each of them, we actually perform the exact regression in terms of the exact position of this bounding box, and also so that way we obtain this 5 different number to perform our regression on, and then this C is the class number, right? And then in this case, we assume that even though we have all the different bounding boxes coming from that single grid or that particular grid, we assume that their classification label is fixed as a single one. Okay, so in that sense, at the softmax layer, if we classify between among the 3 of them, then for each of these bounding box or each grid will be classified into 3 of them, and thus our output is C times 7 by 7, right? And then for each of them, we actually perform the regression on to obtain this 5 different numbers. And so in this case, you guys why is it not the XY and WH, but why do we see dx, dy, and dh, dw. So here the actual number that as our target variable for our regression task is actually the difference. Okay, so for example, let's see. Yeah, suppose we want to detect this pillow, and this pillow has this bounding box as a ground truth. Okay, and then now center that this grid, and then suppose our base bounding box is chosen as this guy. Okay, so in this case, dx, okay, dx is defined as this guy, the difference between the current base bounding box position and the ground truth bounding box position. And so if it is having maybe 7 pixel difference, and then the ground truth is actually on the left of this current bounding box, and so dx, the ground truth is -7. Okay, so that is the actual target variable that we perform our regression on, right? So that way we obtain this relative position difference and also relative size difference, okay, with respect to the original base bounding box. And then what is the confidence? What's the target variable of this confidence value? So in this case, yeah, I mean, that's how this detection module is a little bit heuristic and so-called hairy. So that confidence is computed. I mean, the ground truth for that confidence for our regression is defined as follows. So this is our base bounding box, and this is our ground truth bounding box, right? And so, yeah, purely looking at this region, okay, can you make sure that this bounding box is definitely belonging to pillow? It is not, because it actually involves maybe some hair of dogs, right? And so in that case, that base bounding box may not be classified as purely a single class, right? So in that case, in the beginning, from the beginning, how do we specify the ground truth of this class label of that bounding box? Okay, so for example, like this part is overlapping part with the pillow, and maybe this part is overlapping with our dog, right? So in this case, which one has the largest region? Okay, what's the major category that occupies this region most? Okay, so that is pillow, right? So that's how we determine the ground truth class. But at the same time, it is not pure, right? It's not perfect. So in this case, yeah, we can think of like for this bounding box, what's the ratio of this majority? Okay, it could be 80% out of 100, or it could be maybe only 30%, right? If it is involving many different class objects, and then only 30% might be the top one, right? Okay, so in this case, we just define the confidence as that kind of purity purity value. So in this case, I mean, so given this bounding box, if this one occupies maybe 80% of the entire region, and then the confidence is set as 0.8 for its ground truth. Okay, so although it's a little bit interesting and kind of creative, but it's still somewhat heuristic, right? So that's why this detection kind of algorithms gets a little bit dirty to implement and design. Okay, but anyways, back to the main point or main kind of benefit or advantage of this YOLO and SSD. The main point is that it is assuming the fixed number of proposed regions. Okay, so in that case, the network, we can easily batch them. We can actually apply the batch processing on them, right? Because the number of bounding boxes varies. Sometimes it's 150, and sometimes it's 2,000. And then when running or when training it or when doing the test, yeah, we don't actually know in advance how many number of bounding boxes or the proposed regions will be produced, and so yeah, we cannot easily make the code more efficient. So that's why this YOLO and SSD is much faster than this faster RCNN, because of this fixed number of input to the to this module, or yeah, like this module of like classification and the regression module. I mean, the fixed number of bounding boxes or the base bounding boxes will be given. Any questions?
디텍션 할 때 앞에서 퀘스터 RCN이나 그런 거에서 리전 프로세서를 하고, 그리고 거기마다 원래 트루 레이블을 줘야지 트레이닝이 되잖아요.
네.
근데 리전 프로세서 할 때 쓸데없는 배경이나 그런 거를 잡는 경우에는 트루 레이블을 어떻게?
예, 그러니까 이제 여기서 그가 얘기하는 게, 그리고 저 욜로나 저쪽도 이제 비슷한데, 일단 우리가 이제 그 디텍션, 그러니까 우리가 뭐 그냥 맘대로 고른 그 바운딩 박스가 있을 때, 이게 이제 우리가 오브젝트 클래시피케이션하는 오브젝트가 이제 세 개다. 그러니까 뭐 강아지, 뭐 고양이, 사람이다라고 하면 기본적으로 이 세 개가 다 어느 하나도 포함이 안 되는 이 백그라운드라는 정보가 있잖아요. 그래서 여기서는 항상 그 클래스 개수가 이제 플러스 1만큼, 그러니까 백그라운드라는 클래스가 하나가 더 추가돼요, 이 디텍션 태스크에서는. 그리고 이제 여기서 할 때 이제 그 그라운드 트루스를 어떻게 잡느냐, 그 여기서도 잠깐 뭐 그 저스틴 거기서 얘기가 나오는데, 그 이제 프로포즈된 리전에 실제로 그라운드 트루스 그 디텍션 그 바운딩 박스를 적용했을 때, 뭐 예를 들면 50% 이상 겹친다. 그러면 걔는 그라운드 트루스를 그 클래스로 주는 거고요. 50%가 안 겹친다. 그러면 걔는 이제 other 클래스로 그라운드 트루스를 주는 거예요. 뭐 그런 식으로 이제 바이너리 클래시피케이션을 수행을 하는 거죠, 여기서. Any other questions? Okay, and this mass car CNN, I believe you guys understood this, but yeah, I believe this mass car CNN, I mean, it's still having this it's following the two-stage approach, where the first one is like determining the region, ROI regions, right? And then, yeah, as you see, it almost looked like faster RCNN, because we obtained this convnet, I mean the activation map, as a result or output of CNN, and then we apply this region proposal kind of method, and I think that region proposal method is taking this end-to-end approach of like trainable module of this region proposal network. So masscar CNN certainly includes or involved that module, and then yeah, given this bounding box that was just extracted out by our region proposal network, and then it's not following the YOLO and SSD. So here we cannot assume that we obtain the fixed number of proposed regions. Okay, so it basically follows this faster RCNN framework. Okay, but it's just a kind of multitask learning kind of task. So given the bounding box, we perform the pixel-wise segmentation or classification, whether it is belonging to like given class or not. I mean, whether each pixel is belonging to the given class or not. So so ROI align or pooling is to make the predefined or fixed size of a activation map, right, out of variable size, right? And then the second stage of our conv is actually processing them and then perform the classification among the classification labels. And then if it is classified as dog, okay, so in this case, so as you saw, if it was classified as a cat, and then we determine whether each pixel is belonging to that cat category or not, right? So this part will be classified as a negative label, right? Because that is not belonging to the object of an interest at that particular patch. Okay, so in this case, it is just nothing but the combination of multiple tasks, which is a multitask learning, classifying it, and the pixel-wise classification of it, and then also, also it is doing the bounding box regression on that as well. Okay, and then also we can even add additional task of this pose estimation, right? So it's like doing all the tasks simultaneously, such as this classification and the bounding box regression and the pixel-wise classification, and finally the pose estimation. Okay. Any questions so far? Okay, then let's move to the next chapter. So do you guys understand why we only see the color image at the first layer and but not on the second or the later layers, right? So in this case, so yeah, each image over here is actually composed of 3 different convolution filters, right? Corresponding to RGB, right? So in this case, in the next layer, we see one single parenthesis is corresponding to one single filter, right? So it is indicating a different channel, right? Okay, so because in the second layer or later layers, we cannot assume that the first channel is corresponding to RGB, and so we cannot easily combine them into a colored map. But in the case of first layer, the first channel of our comp filter is corresponding to RGB, and so we can just assign that color and then just overlay them to obtain the single color, colored filter visualization. So I'd like to discuss a little bit on this visualizing the activation. So this was only, this is 2014 paper called Deep Viz Toolbox. So okay, so so have you okay, so so this is an input image, although it's like a streaming kind of video. Let me just spend just 1 more minute, and then this is the overall layers that we have in our CNNs, and then we chose that the first combo layer, and then there are regular grids like all the rectangles, and each of them is visualizing the activation pattern given this particular image. And then in this case, we have we have in this one layer, it has like a 64 channels as an output, and then at each slice we have a 2D matrix, right? And then these are kind of an activation pattern. And then given this image, yeah, for this particular filter or this particular channel that was produced by a particular convolution filter, right? And that convolution filter is generating the highly activated value or high activation value along this position, and that position is corresponding to this guy, right? And then in this case, this filter is actually playing a role of detecting this vertical edge, right? So there is some interesting. Okay. Give me 1 second. Yeah. Give me just 1 second. So. Okay. So, yeah, although so this time is over, so I'm sorry, but it's really interesting. So I'd like to finish it with this description. So in this particular case, we chose some relatively higher layer, right? And then these are all different filters. And then in this case, this is the enlarged version of that particular activation. Okay. So the filter that would generate that particular activation is actually detecting the characters, okay? The characters in this real world image, right? So I thought it's really interesting because that can be used as like OCRs applications. So given a particular image, and then where is these character or sequence of the text found? Okay. So that filter plays of that interesting role. Okay, so I strongly encourage you to just watch this video. So yeah, that's it for today's class.
질문 중에 제일 위에 있는 거 예전에 제가 여쭤봐가지고 그거 없애주셔도 되고 네, 한글로 달라고.
아, 네네. 그 오토인코더요?
네.
네, 그래요. 이거 설명을 좀 했었던 것 같아요, 그죠?
네, 제가.
네. 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 아, 네. 네. 네.
먼저 여쭤봐.
네.
그 컨피던스 부분이 약간 이해가 안 돼서 그러니까 예를 들어서 저희가 그러니까 욜로에선 저희가 박스를 정하잖아요.
네.
그래서 저희 박스를 정했는데 그게 뭐 도그는 그 박스에서 80%에 해당하고 캐시 20%에 해당하면
네.
컨피던스가 0.8이라고
네.
하셨는데
네.
그러면 이게 왜 굳이 필요한지가
그게 왜 필요하냐면 이제 그러니까 여기에 뭐 예를 들면 30%만이 이제 도구로 있어요. 근데 그거를 뭔가 도구로 그냥 클래시피케이션을 하면 뭐 그래도 되는데 그건 이제 어떻게 말하면 도구라고 이렇게 명확하게 이야기하기엔 좀 애매하잖아요. 애매하니까 이제 어떤 주어진 바운딩 박스에 대해서 그거에 대해서 머저러티 클래스, 그러니까 리전으로 볼 때 가장 넓은 영역을 차지하는 그걸로 클래시피케이션을 하도록 하지만 그거 자체가 이제 그 좀 노이즈할 수가 있기 때문에 좀 애매할 수가 있기 때문에 이 모델한테 이거는 내가 캐시다라고는 이야기하지만 이게 이제 캐시 차지하는 정도는 별로 안 된다라고 하는 거를 좀 이야기해요. 그거를 익스플리시트하게 그러니까 명시적으로 그 밸류를 직접적으로 슈퍼바이즈를 함으로써 가르쳐주면 얘가 뭔가 좀 뭐 캣이 조금밖에 안 등장했는데 이걸 뭐 전체를 다 캣으로 뭔가 인식을 한다거나 그런 식의 좀.
근데 어차피 XY 이거 HW로
네.
이걸 백월드를 하면은
네.
어차피 그 박스로 가지는 거 아니에요? 근데 컨피던스라는 거 자체가
네.
예를 들어서 뭐 더그에 맞추려고 하면 그 더그에 대한 XY, H 그거에 맞춰서 이렇게 가는 거 아닌가요?
네, 맞아요. 네.
근데 그러면 그래도 가는데 이게 뭐 컨피던스 이게 얼마나 확실한지 안 확실한지 그냥 그 지표에만
그러니까 이제 뭐 이렇게 그 베이스 바운딩 박스가 주어졌을 때 그거 딱 안쪽에 있는 것만으로 잡히진 않고 이렇게 삐져나갈 수가 있잖아요. 그러니까 이게 아까 여기 강에서도 이렇게 나왔지만 DX나 DY 뭐 이런 것들이 이제 이 바깥쪽으로 삐져나가는 식으로 이렇게 프리딕션을 할 수도 있어요. 그럼 여기 이제 뭐가 있는지 모른 채 그냥 대충 아 강아지가 이 정도로 지금 동그라미가 있으니까 여기서 조금 더 가서 이 정도까지가 있겠구나라는 것을 예측을 하게 되고요. 네. 그 다음에 네, 뭐 하여튼 그렇게 하고요. 그래서 완벽한 정보가 다 주어진 채 하는 게 조금 아니라는 것과 그 다음에 여기서 이제 저 컨피던스를 저걸 어디서 쓰냐 하면 기본적으로는 이게 들어오면 그러니까 이 테스팅 타임에 생각을 해보면 이제 그 패치들을 다 넣어갖고 거기서 이제 실제로 오브젝트인 것과 아닌 거를 바이너리 클래시피케이션을 해야 되는 거잖아요. 그거 할 때도 아마 그게 그 컨피던스가 얼마 이하가 되면 그걸 이제 그냥 버리는 거죠. 그런 식으로 사용하고. 약간 나도 정확한 풀 디테일은 지금 설명을 못하는데 왜냐면 저쪽에서 어덜 클래스가 분명히 있어요. 그 클래스 클래시피케이션 할 때. 그래서 거기서 어덜 클래스로 하면은 그거는 버려야 될 거고 거기서 어떤 걸로 하면 그건 우리가 취해줘야 될 것도 맞긴 해요. 근데 이게 또 중요한 게 그 SSD도 보면은 이게 같은 리전에서 여러 이렇게 버전의 그 베이스 바운딩 박스를 만들어 집어넣잖아요. 그러면 이게 어떻게 보면은 얘들이 이거는 하여튼 캐시라고 나왔으면 여기서 요거를 넣었을 때 그 DX, DY가 약간 요렇게 됐고 또 다른 slightly different한 그 베이스 바운딩 박스를 넣었을 때 또 그 DX, DY가 정확하게 일치하지 않을 수 있잖아요. 걔네들 판단 결과. 그러니까 이런 식으로 이 판단들을 뭔가 다 테스팅 타임에서 그러니까 트레이닝에는 문제가 없었지만 테스팅 타임에서 이런 좀 약간은 컨플릭팅하는 이런 결과들을 합쳐서 뭔가 최종적으로 가장 그래도 좀 정확도가 높은 방향으로 뭔가 해줄 그런 휴리스틱 같은 게 또 필요해져요. 그래서 그런 거 할 때도 뭐 쓰는 알고리즘들이 여기 좀 더 들어가거든요. 네. 그래서 약간 좀 지저분해요, 이쪽.
알겠습니다.
네.
감사합니다.
네.
그 수업 쪽에는 아니고 그냥 개인적으로 여쭤보는 건데
네.
저희가 이번에 지난 월요일에 들어온 강의에서 크리티언트 어센트 하면서 애드버서리 이그젠플에 대한 얘기가 나왔잖아요. 그런 애드버서리어란 이그젠플이
네.
약간 특정 레이어의
네.
그 그레디언트 값이랑 조금 더 연관돼서 나올 가능성이 클 수가 있나요?
그렇죠.
보통은 하위 레이어보다 상위 레이어 쪽으로 추정돼서 관련이 있을 가능성이 있나요?
네. 그러니까 일단 adversarial example은 우리가 이제 그 그레이디언트 어센트를 할 때 그 스타팅 포인트가 되는 그레이디언트가 그 클래스에서 시작을 해요.
네네 제일 맞아요.
그렇죠. 거기서 이제 우리가 다른 클래스로 의도적으로 다른 클래스로 미스클래시피케이션이 되도록 만들어주고 싶으니까 그러니까 이게 뭐가 적대적인 이야기라는 게 들어가는 거예요. 근데 이제 결국 그레이디언트 어센트라는 건 그 노드의 액티베이션 값 혹은 그 노드 값을 최대한 키우도록 하기 위해서 우리가 뭐 그걸 인풋 단에서 하겠다 그러면 그레이디언트를 쭉 흘려갖고 인풋에 해당하는 그 픽셀 밸류에 대한 그레이디언트를 구한다. 그러면 그 그레이디언트를 가지고 인풋 이미지를 조금 업데이트하면 그 어떤 우리가 이제 다른 얼토당토하는 다른 클래스의 스코어를 더 높일 수 있도록 하는 거죠. 근데 이제 중요한 건 지금 얘기했던 것처럼 이 미들 레이어에서 또 어떤 그 레이어에 혹은 어떤 그 채널이나 뭐 그거가 더 이제 이거에 영향을 많이 미치냐? 이것도 당연히 나와요. 그러니까 이거 값을 늘리기 위해서는 백프라블 할 때 우리가 실제로 그 그레이디언트를 구해서 저기 그 그레이디언트 어센트를 하는 거는 그래서 실제로 직접적으로 업데이트하는 그 베리어블들은 이제는 그 우리가 이미지에서 갖고 있는 픽셀들이겠지만 그렇지만 우리가 그 모니터링 용도 아니면 이제 뭐 언더스탠딩을 하는 용도로 이 중간 레이어에서 그때도 어쨌건 백프랍은 이제 지나갔을 거고 그 중간 레이어에서 각 채널별로의 뭔가 그 그레이디언트가 얻어졌을 거잖아요. 그러면 그 값을 뭐 이렇게 통계를 내서 보면 이 채널에 이제 할당된 그레이디언트가 일반적으로 다른 채널보다 더 크다. 그 말은 이 채널이 얘를 이 애드버서리얼 example로 만들어 주는데 더 직접적인 영향을 더 많은 영향을 끼친다는 애니까.
감사합니다.
네. 네.
교수님
네.
혹시 그 저희 텀 프로젝트 관련해 가지고 방향이 좀 어떻게 해야 될지 모르겠어 가지고